Greetings and salutations. Welcome to today's recording on 2019's Level 2 Organic Chemistry. We will get into the topic. Let's, again, like always, one question per video, and we are looking at question 1 in this particular recording. Okay, so let's get started. So very typical question that you get in organic chemistry. The first part is an achieve question, is to name and to draw. Okay, so you got 4 boxes. In this case, you needed 2 to pass, and we are going to get all of them correct. Now, first thing first, you have to know your functional groups. So if I see COOH, so that tells me I have a carboxylic acid functional group. Okay, so to name a carboxylic acid, you have to know the suffix, which is something enoic acid. So we need to count the number of carbons. So this is carbon number 1, carbon number 2, carbon number 3, 3 carbons. So it is going to be propanoic acid. You don't need to say propan-1-noic acid because the carbon that has a OOH bonded to it is always carbon number 1. Okay, now next part, propan-2-amine. Now with drawing, I think it's much easier to draw because I always recommend you to do the carbons first. So propane means 3 carbons. On the second carbon, you have an amine. So on the second carbon, you have an NH2. And you just make sure that every single carbon has 4 bonds. And that's how you draw carbon propan-2-amine. All right, next one. So you have 2 functional groups here. So you have a double bond, CC double bond, and you have a Cl as a branch. So we don't really care about all the carbons and hydrogens. We always prioritize our functional group. So the double bond CC is more important than the Cl because the Cl is, you can treat it as a branch, whereas the double bond is far more reactive. So with naming, we got to make sure that we prioritize the double bonds first. So this is going to have, we're going to have 1, 2, 3, 4, 5 carbons, so it's pent. And where is the double bond? The double bond is going to be on the first carbon, which gives us the lowest carbon count. And now we're not done yet. We need to address the chlorine. So if that was carbon number 1, then there will be 2, 3, 4, 5. So the Cl is bonded to the 5th carbon, so it will be 2 chloro pen 20. I couldn't fit it in one space, but you get the idea. And it needs to have a hyphen there. So 5 chloro pen 20. Now last one, 2,3-dimethylbutane. So again, work backwards. Look at your carbon chain first. So but is 4. So 1, 2, 3, 4. 2,3-dimethyl. So on the second, on the third carbon, I have 2 methyl groups. So on the second, on the third, I have 2 methyl groups, which are CH3s. And then you have to make sure that every single carbon has 4 bonds. Okay, very easy, achieve question. So let's move on. Next one, draw 4 structural isomers of C4H10O. So that means our molecule needs to have C4H10Os, and they are alcohols. Okay, so they are either primary, secondary, or tertiary alcohols. So let's just draw as many as we can. Now, with these type of question, I always tell my students just to do the carbons first. Don't worry about the H's, just try to build the skeleton. So if I put the OH group here, and then if you do the other carbons, you do CH2, 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 CH3, then you count, and that would be 10 hydrogens. So that's this is C4H10 and 1O. Okay, so that's the easiest one to draw. As you can see, I did the carbons first, and I did the hydrogens last. Okay, so this is going to give us a butane 1O, and this is going to be a primary alcohol. Why is that a primary alcohol? Because my OH group is bonded to a carbon which is bonded to one other carbon directly. Next one, so we have the freedom. Now we can just move the OH group from the first carbon to the second carbon. Then you get that. Now don't get confused and do this, and you're like, oh, I can do another one. I just put the OH here. This and that are the same thing. Okay, so just draw one of it and that will be fine. Now, so this is our first isomer, this is our second isomer. We can do another one, we can do C. Now once you have run out of space, like say you have 4 carbons as your longest chain, and you have nowhere else to put your OH to make a new molecule. So cut down the carbons from 4 to 3, and put the carbon as a branch and see where you can fit the OH. So I can fit the OH here, which will give me 2-methyl propan 1-ol, or I can I can have the carbon skeleton but then put the OH here. Okay, so let's perfect these. So for the second one, I'm going to have CH3CH OH CH2 CH3, which is going to be this particular structure, and this is a secondary alcohol. Why? Because my OH group is bonded to a carbon which is directly bonded to two other carbons. If I draw number 3, it's going to look like this, and then I'll just again make sure every single carbon has 4 bonds. So this is going to be another primary alcohol because my OH group is bonded to 1 carbon which is directly bonded to one other carbon, so this is going to be primary. Now the last one we'll do is CCCOH on the second carbon, so this is methyl propan 2-ol, and we will have what we call a tertiary alcohol because your carbon, your OH is bonding to a carbon which is bonding to 3 other carbons, so that's why it's a tertiary alcohol. Okay, so pretty straightforward. Now let's move on to C. So refer to the compound in the table below to answer part I to IV. So we're looking at these 2 structures. So the first one is butane, and then B is butane. Very straightforward. Now we have to draw the cis and trans isomers for A. Now people, cis and trans isomers is a guaranteed excellence question in the exam, so it is important that you know what you're looking for these type of questions. Okay, how do you draw cis and trans isomers? So you need to have a double bond. So this is how I'm going to draw this. All right, so I'm going to show you how I will transform this image. So instead of drawing it like, you know, this the skeletal image, you know, in everything in a straight chain, I'm going to rearrange it. I'm going to highlight the carbon so you can see which one I'm looking at. This yellow carbon is this yellow carbon, and this green carbon is this green carbon, and you just need to think about what they're bonding to. So this yellow carbon is bonding to an H, so this H is this H, and then the CH3 is that CH3. Okay, so on the other side I'm going to do exactly the same thing. So what I've just done, I centralize my CC double bond and I drew everything around it, one up, one down. Now this is a cis molecule because everything is on the same side, and that's cis. Now how do I draw trans? Very straightforward. You just keep one side the same and flip the other side, and this is trans because everything is on the opposite side. So if we come back and draw it here to give us a proper answer. Now it's very important, guys, that you make sure that you do the first step, like as in put the CC double bond in the middle if you're not so confident with this particular part. Okay, so how do we name this? This is cis butane. Now make sure you put cis there, and this is going to be trans butane. And explain why A exists as geometric isomers but B cannot. I've typed out the answers below, but I just want to go through the bullet points really quickly. You are looking at 2 bullet points you must have. If you were to have geometric isomers, you must have CC double bond. Okay, so the double bond prevents any rotation around the double bond. So if you know, I'd love to have monomers to show you, but if everything was single bonded, the molecule, the atoms around the single bond can freely rotate, and that will just, you know, it may look different from one moment to the next because it has rotated. It doesn't mean it has changed the structure. But if you have a double bond, that means these atoms, you know, these groups of atoms bonding to the double bonded carbon will be locked in that place. They can't rotate around the CC double bond. And the next part is that each group of atoms, probably not each group, so the group of atoms bonding to each carbon in the CC double bond must be different. Now you don't have to have both sides to do this. Let's say if I were to draw, let's try about these. If I were to, I'm just going to give you some examples. Come on, robot quicker. Okay, so if I were to give you, like, say something like CH3, CH3, H, CH3, and I go, does this have geometric isomers? So what you need to do, you need to look at the 2 carbons in the double bond, and then you need to look at the atoms, the groups of atoms bonded to each C. So you can see the 2 highlighted atoms are the same. So this doesn't have geometric isomers. Okay, so this doesn't have geometric isomers. Another example, I mean, this ones that we've done here, you can see that the CH3 and H are different, the CH3 and H are different, and then if you have them on the same side, you have a cis isomer. Sometimes they give you questions like these trying to confuse you. I personally haven't seen it for level 2, but they can if they really want to be mean about it. Like, say something like this. And this is where people, you know, to complain and say, you told us this H and CH3 are different, and you told us the Cl and CH2 CH3 is different, so this must have cis and trans isomers. Well, no, because yes, these 2 are different, these 2 are different, but then these 4 different groups, none of them are the same. So when we're talking about cis and trans isomers, you need to have at least one couple of atoms, you know, group of atoms that are the same, and then if they were on the same side, it's cis. If they're on the opposite side, it's trans. Okay, so this is a guaranteed question, guys. Very, very popular. If you don't trust me, go through the past 5 exams, you're going to find this question in every single exam paper. Okay, so spend some time to learn it. So here's my answer. So in order for molecule to have geometric isomers, it must have 2 required features. Okay, so it must have a CC double bond, which prevents rotation around it, and then the group of atoms bonding to each carbon in the double bond must be different. Now, if we link back to the question, so it is important that you link back to the question. So the question is asking you, why does A have geometric isomers? Because it has both required features, but compound B doesn't have any of these, therefore it does not have geometric isomers. Okay, so hopefully this is straightforward enough. I think it's really generous for this to come up every year for an excellence opportunity. So if you weren't so confident before, just make sure you go watch this particular section a little bit more, then hopefully you get it. Okay, next part. Explain how acidified potassium permanganate solution can be used to distinguish solute compound A and compound B. Now I put A and B next to these so we can, you know, clearly look at what functional groups we're dealing with. So the first one is alkene, the second one is an alkane. Now you need to remember, now a lot of organic chemistry is rote to learning. So first thing first, you need to know that potassium permanganate is purple. And if you did well in redox, you understand that if it was to undergo oxidation reduction reaction with the other thing, so this will go from purple to colorless. Okay, so which one would it react? Well, if you look at the flow charts that your teachers have given you, you will know that if you have the alkene react with the KMNO4 /H+, you will know that the double bond will be broken, and then you will make what we call a diol. Okay, so what is a diol? Diol means you break the double bond and you add 2 OHs onto them. Now, one thing that I've always suggested my students to do is, yes, memorizing the flow chart is important, but you may not necessarily get the grades you want just because you memorize a flow chart. You have to understand how to apply it, and distinguishing test is a really good way for us to identify what if you have understanding of that or not. Okay, so just think about the flow chart. With the alkene, every single reaction that the alkenes do with the double bond is breaking the double bond. So if you remember that, it's not going to, like, this carbon is not going to react, this carbon is not going to react, you know, they're not going to react because they're not the function group. It is always the function group that does something. Okay, so this is an oxidation reaction because you are gaining oxygens. And what is a relevant observation? You are going to see purple to colorless. What about compound B? No reaction, stays purple. Okay, so here is the Here's the answers. So the potassium permanganate will go from purple to colorless because it's an oxidation reaction, because you make a diol, the CC double bond is broken, and the other one there's no change with B, so it will stay purple. Now a lot of people just, you know, for something to have no color change is actually an observation as well, because nothing actually happened, so there's no change, so that is an observation. So it is important to include that in your discussion if you are asked. Last bit for this. Okay, so compound A and B both react with bromine water, and compare and contrast this reaction by referring to the conditions required, the observations, products formed, and the type of reaction. So the first one, so A is butying. Again, this is a very standard question. So if we add bromine water, what is going to happen? Again, hopefully you understood what I was talking about just now. You will always break the double bond. And what do you do with the Br2? You break the double bond. The two carbons here are no longer fully bonded, so the two bromine atoms are added into the molecule. This is why this particular reaction is called an addition reaction, because the Br2 atoms are being added into the molecule. You break the double bond. Okay, so what is the condition required? We need Br2. What is the observation? So you will see a color change. Br2, the Br2 will go from orange or red or brown, whatever, you know, we accept all those colors, from orange to colorless. Now the key thing here is that it does it straight away. Okay, it's because it is a really fast reaction. It happens straight away. The products formed, done that. The types reaction, done that. Now for B, for CH3, CH2, CH2, CH3, which is an alkane, if you add Br2, nothing's going to react because you need the UV light. The UV light acts as a catalyst, and what that does is that now you can replace any of these hydrogens you want, but I normally just replace the hydrogen at the end. Now I'm going to use a different color just to indicate that the Br, and so what happens is that one of these H's and one of the Brs, well, one of the Brs substituted into the carbon. It's like if you play sports, you know, your manager or your coach says sub please, so the Br gets substituted in, the H didn't play so well and gets substituted out, and that guy decided to sit without the Br, and that's your HBr. So you didn't break anything. This is why this is called the substitution reaction. And the observation is also going to be Br2 turning from orange to colorless, but then this particular reaction will be much slower. So this does it in like say 3 to 5 minutes. It is a much slower reaction. Okay, and we've done all of those, so here's the answers. As you can see, I like drawing them out. If you draw them out and, you know, instead of naming it 2,3-dibromobutane, you can just draw it and just show, hey, that's my products. Okay, so the key thing here, when you add, so this is a fast reaction, it goes from red, orange to colors straight away. It is an addition reaction because you're breaking the double bond and the two Br atoms are added. When you're dealing with Br number B, compound B, you need UV light as a catalyst, and therefore you go from orange to colorless in a few minutes under UV light. It is a substitution reaction because you substitute one H with one Br. Okay, very standard question 2019. So I think these questions are quite standard. So make sure you go through them, make sure you understand what we're trying to do here, and we'll be moving on to question 2 in the next video. Okay, study hard, take care, and bye bye.